right, in this section, we want to look at the properties of logarithmic functions. We are going to convert from logarithms of powers and products and quotients to expressions in terms of individual logs. We're going to condense and we're going to expand. The first thing we want to look at is logarithms of products, and I'm just going to abbreviate with logs of products. Save a little bit of time writing that out. Okay, now remember that when we first defined a logarithm, we said that a logarithm is an exponent. So we're going to use the properties of exponents to help us in finding the properties for logarithms. And remember that if we have the same base, if we have a to the m times a to the n, and we want to simplify that, we simply add the exponents. And the same idea is used with the product rule with logarithms. In other words, the log base a, it doesn't matter what the base is, of m times n is equal to the log base a of m plus the log base a of n. The logarithm of a product is the sum of the logarithms of the factor. So if I wanted to rewrite log base 3 of 9 times 7 and simplify that, or 9 times 27, excuse me, without using a calculator, we can get a value here because we have a specific base, and you're going to see that we're able to calculate this. This becomes the log base 3 of 9 plus the log base 3 of 27. Now I'm not finished here because I can rewrite 9 as 3 squared plus the log base 3 of 3 cubed. And I think we had talked about this a little bit. If not, we'll talk about it a little bit more in just a bit. But if these two match, this is equal to 2. And if these two match, this is equal to 3. And we get that this value is equal to 5. Let's do another one just to get a little bit more practice. Let's look at the log base 5 of 5 times 125. Well, I can first expand, and we get the log base 5 of 5 plus, the log base 5 of 5 plus the log base 5 of 125. Well, I can rewrite the log base 5. Now we know that this is to the first power, plus the log base 5. 25 is 5 cubed, and this becomes 1 plus 3, or 4. Now the only reason that we can get an actual number here is because we have the same bases. Here we had a base of 3 and a base of 3, and here do a different color. See, we had the base of 3 and the base of 3, the base of 3 and a base of 3. Here we had a base of 5 and a base of 5, and same thing here. That's the only reason that we could actually get a number. If we weren't able to get with the same base, we couldn't simplify it quite this far. Okay, now let's go the other way. Let's see that if we have it expanded, how we can condense. I have the log base 2 of p cubed plus the log base 2 of q. And I want to condense this. In other words, I want to write it as a single logarithm. Well, because this is added, we know that that indicates to us that we want to multiply. So we're going to have the log base 2 of p cubed q. Log base 2 of p cubed q. So let's look at another one. Let's say that, I'm looking for one that's simple to look at. Let's say that we had the log base a of 75 plus the log base a of 2. Well, again, because this is addition, we can rewrite as a single log using multiplication. And 2 times 75 is 150. Notice we can't simplify any further than that because our base is a. There's no way that we can rewrite 150 with the base of a. Next, we want to look at logs of powers. Logs of powers. And we're going to think about the power rule using exponents. If a logarithm is an exponent, then we can use the idea of the properties of exponents. And if we had a to the m times n, raised to the n, that becomes a to the mn. We multiply. So if I have the log of m to the p power, I can simplify this by moving the p to the front, p times the log of m. And we can see how that worked when we had the log base 3 of 3 squared. Well, that, if I simplify, that becomes twice the log base 3 of 3, which is simply 1. So let's look at a couple of examples here. If I had the log base a of 11 to the negative 3, and I want to rewrite that using the power rule, it becomes negative 3 times the log base a of 11. Here I have the log base a of the 4th root of 7. Well, I can rewrite that as the log base a of 7 to the 1/4, remember, and simplify by taking 1/4 log base a of 7. Just one more. If I had the natural log of the cube root of 4, well, I have to remember that I can rewrite the cube root of 4 as 4 to the 1/3. So applying the product rule, we get 1/3 times the natural log of 4. Okay, so far I think you can see that these are really fairly easy properties to apply. Let's look at the log of quotients, or logs of quotients. Again, we go back to our exponential rules. It says if we have a to the m over a to the n, we can simplify by taking a to the m minus n. And we will use that same idea with logarithms. If we have the log base a of m over n, this becomes, if I expand it, it becomes the log base a of m minus the log base a of n. So if I wanted to express the log base t of 8 over w, I could write this as the log base t of 8 minus the log base t of w. Let's look if I have the log base 5 of x over 25, and I want to expand this or write it as the sum or difference of a logarithm. Because we're dividing, it's going to be a difference. We're going to have the log base 5 of x minus the log base 5 of 25, but I'm not done yet, because here I can simplify some more. And when you can simplify, you need to simplify. This becomes the log base 5 of x, and I can rewrite 25 as 5 squared, and we've seen two different ways that we can simplify. This becomes minus twice the log base 5 of 5, and the log base 5 of 5, of course, is 1, so our solution is the log base 5 of x minus 2. So notice here I could simplify, so you need to do that. Another one that you'll see a lot is log base 2 of 8. Well, we know that log base 2, 8 is 2 cubed, and so this becomes 3. Now we worked with expanding. Let's condense or express as a single logarithm. If we have log base b of 64 minus log base b of 16, because this is subtracting, I can rewrite this as the log base b of 64 divided by 16, which is the log base b of 4. We can simplify that. Okay, let's look at the log of x minus the log of y. Remember, because we don't have a base listed, this is base 10. But if I want to write this as a single logarithm, it becomes the log of x over y. And that's all we do there to condense that logarithm. Now there's some errors that I want to be sure that we don't make. So these are errors. I'm going to do these errors in red. Hopefully that'll remind you. But these are errors. The log of m times n, log base a of m times n, is not equal to the log base a of m times the log base a of n. That's a common error. Those two are not equal. Remember, it's not the product, it's the sum of logarithms. And likewise, the log base a of m plus n is not equal to the log base a of m plus the log base a of n. I bring this up because a lot of people make these errors. The log base a of m over n is not equal to the log base a of m over the log base a of n. It's equal to the log base a of m minus the log base a of n. And likewise, the log base a of m, the whole thing raised to the p power, is not the same as p times the log base a of m. It's only if the m is raised to that power. So these are some common errors that you need to be sure and avoid. All right, we're going to look at some that are just a little bit more complicated. You know, things don't always stay as easy as they first appear. Let's express each of the following in terms of sums and differences. Okay, I'm going to start with the log base a, and I'm doing my best not to hit the mute button. x squared y to the fifth over z to the fourth. Well, remember, division means we're going to subtract, multiplication means we add. So this, if we break this up, I'll just do it in stages. The log, this becomes the log base a of x squared y to the fifth minus the log base a of z to the fourth. Well, we can expand some more. This is the log base a of x squared plus the log base a of y to the fifth minus the log base a of z to the fourth. And we're not finished because we can move that 2 to the front on the first term, the 5 to the front on the second term, and the 4 to the front on the third term. So that is expanded completely. All right, let's look at another one. I want the cube root, log base a. Don't want to forget that. The log base a of a squared times b over c to the fifth. And we want to expand this one. Well, the first thing I can do is rewrite this as a squared b over c to the fifth. All of that is to the 1/3. So I can rewrite next, taking it a step at a time. This is going to be 1/3 the log base a of a squared b over c to the fifth. Now, the more familiar you get, you can combine a lot of these steps together, but I want to be sure that we all see each step so I don't lose you somewhere. So this can become rewritten as 1/3 the log base a of a squared b minus the log base a of c to the fifth. And we can expand again. And I'm going to have the log base a of a squared, but I'll go ahead and put that 2 in the front, plus the log base a of b minus the log base a of c to the fifth, but I can move that 5 to the front. And then we can take it one step further. Log base a of a is 1, so we have 2/3. You want to simplify that. Plus 1/3 log base a of b minus 5/3 log base a of c. And we have gotten that completely expanded. Okay, the next thing we want to do is express as a single logarithm. So let's say that we have 5 times the log base b of x minus the log base b of y plus 1/4 the log base b of z. Now, one thing I want you to notice, there's not any parentheses around the last two terms. So let's just do this first. Log base b of x to the fifth. And I'm going to rearrange these since I don't have them grouped in parentheses. Plus log base b of z to the 1/4 minus log base b of y. You don't have to do it that way. It just kind of helps us see what we're doing here. So we're going to have the log base b of x to the fifth times the 4th root of z over y. And we have taken that expanded logarithm and condensed it or written it as a single logarithm. We'll do one more like that. Okay, let's take the natural log of x squared minus 4 minus the natural log of x plus 2. Well, we are subtracting, so I can rewrite that as x squared minus 4. Remember, natural log has a base of e over x plus 2. But I'm not finished because I hope you remember difference of squares. This becomes x plus 2 times x minus 2 over x plus 2. And so when we fully condense, we get the natural log of x minus 2. Okay, I have given you some values for log base b of 2, log base b of 3, and log base b of 5. And we're going to use these values and expanding logarithms, properties of logarithms, to get some actual values. For instance, I'm trying to do problems that are very similar to what you're going to have on your homework. If I have the log base b of 125, now I need to see if I can rewrite that in either terms of 2, 3, or 5 using properties of logarithms. Now I do know that I can rewrite 125 as 5 cubed, and that becomes 3 times the log base b of 5. Now I've been given a value for the log base b of 5. So we're going to have 3 times 1.609, and you can just plug that straight into your calculator, and you get that that is approximately 4.827. And I did that using the values that I was given and the properties of logarithms. If I wanted to find the value of the log base b of 5 over 3, well, I can rewrite that using my properties. Log base b of 5 minus the log base b of 3. And I was given values for that. So we have 1.609 minus the log base b of 3 is 1.099. And that is approximately 0.51. Just plug that straight into the calculator. Let's look at another one. I want to keep those values handy so I can look at them. All right. Let's say we want to find the log base b of 1 over 6. A couple of ways we could do this. Let's, we'll look at one way and then we'll look at the other. Log base b of 1 minus the log base b of 6. Well, the log base b of 1 is 0. And we can, oops, I don't need an equal there. And we can subtract. Well, I can write the log base b of 6 as 2 times 3. And if I expand that, we're going to have the log base b of 2 plus the log base b of 3. And we can just plug in our values, 0.693 plus 1.099. And we should get a negative 1.792. That's the approximate value. The other way that you could do that, and I won't work through the whole thing with it, but we could look at this as the log base b of 6 to the negative 1, which becomes a negative log base b, and then we could do the 2 times 3, and that gets us right back to where we did on the previous problem. Okay? one more. Let's say that we had the log base b of 15b. Now, I don't have a value for 15, but I do have a value for 3 and 5. So I could rewrite this as the log base b of 3 times 5 times b, which becomes the log base b of 3 plus the log base b of 5 plus the log base b of b, which is 1. So the log base b of 3 is 1.099 plus 1.609 plus 1. And that, when we add them all together, is approximately 3.708. Okay, just a couple of more things. We've already talked about some of these, but just as a quick review, the logarithm of a base to a power, if we have the log base a of a to the x, that equals x. And we could prove that. You could use that product rule. This becomes x times the log base a of a, which we know this is 1. And so that's the proof of that. But if we want to look at some, the log base a of a to the 8th is simply 8. If we have the natural log of e to the negative t, well, this base for the natural log is e, so the bases match, and this is equal to negative t. And the same thing if we have the log of 10 to the 3k, well, the bases are the same. The base of the logarithm, the common log, is 10, so this equals 3k. This is the rule. If these bases match, then these two match. And then one more rule we want to look at. It's another very simple one. And it says that if we have a to the log base a of x, that equals x. If these bases match, then these two match. So if I had the log, 4 to the log base 4 of k, we get k. And the reason these two problems work that we just did is because exponential functions and logarithmic functions are inverses of each other. And remember, we said if we take the composition of those functions, we get x. And that's really what we're doing here. We're taking the composition of the function. E to the natural log of 5, well, the base is the same because the base of the natural log is e. This is simply equal to 5. All right. Your assignment, this is assignment number 4. Is on page 355. 4 to 44 every fourth. 54 and 56. And 68 to 74 even. All right.